Welcome to this next lecture on acoustics. We have been looking at exterior sound and we have looked at a lot of spherical coordinate problems. Okay. We will do a explanation of the physics in the next few classes, but before that I want to point out one thing, that this KH integral, which is say of this form, which is of this form, okay. So we know the green function and we know derivatives of we know information about phi and del phi on the surface. So this surface is hypothetical. It's not, it need not be real. So what I mean is, suppose I have a region of space bounded by a surface S and I have a source over here, and I can find the value at some location r dash, pressure value at some location r dash due to the source. And that is one, so that I will call it directly finding the pressure, directly finding the pressure. The other is I find the pressure on a surface and also del P by del N, the normal gradient, which is velocity on this surface everywhere. Then I use that information in the KH integral equation. Then both these answers will be same. Okay. So what this says is that this surface can be just a notional surface on which you find the two bits of information, del phi dot n and phi. Okay. So we will take a simple example to prove that. Okay. So this is the scenario. I have a sphere of radius a, okay, and then at a distance of r dash, at a distance of d from the sphere, okay, I have a point source. And there is a point denoted by r dash where I would like to know the pressure, okay, and the general roving coordinate on this surface is r. It moves on this surface r, okay, on the spherical surface r. We will later set r equal to a, the radius of the sphere, okay. R will be the general, A will be the specific value. Okay. So now what is the pressure at any general location R bar due to a source at, let us say, D bar? Okay, that would be P, that is equal to some amplitude P0 e to the power of minus j k magnitude of R minus D bar, let us say, by I k magnitude R minus D bar. Okay. Now I will set this entity R minus D equal to xi. Okay. And the scenario is this: this is a spherical coordinate, this is the theta, it is measured theta equal to 0, theta equal to pi over here, and this is the azimuthal coordinate. Okay. So now I can write this pressure due to a point source using a Hankel function. Okay. It is written as this: P of xi is equal to P0 e to the power of minus I k xi by I k xi. Okay. The 4 pi etc. or bringing in the I, they are all absorbed in P0, just a monopole source, pressure due to a point source, the green function basically, free space green function, but written now to accommodate a form of a Hankel function which is equal to minus P0 Hankel function of the second kind k xi. Okay. Now again the green function comes in, free space green function comes in, which we will write as g of r slash r dash. Okay. Now r dash, r as I said will rove on the sphere. Okay. And we will use g on the sphere, and therefore r will be the roving integration variable and r dash is any interior point. So r dash is less than r. So if that is the case, we have seen the green function expansion minus I k summation over n j n of k r dash Hankel function n of k r summation over m y m conjugate n theta dash phi dash y m n theta comma phi. So this location has r dash theta dash phi dash coordinates. Okay. And this location on the sphere has r theta phi coordinates. Now what do we need? My, let us say, P dash, for example, P at r dash is given by integral g del p dot n minus p del g del g dot n ds. So I need g, I need del p dot n, I need p I need del g dot n. These 4 bits I need. Okay. So now if I am going to move on a sphere, okay, on a sphere, then this del g dot n, okay, ends up as del g del r, del g by del r. Okay. Why? Because we are interested in the interior sound now. We are looking at bits of information on a surface, actually a spherical surface, so that we can go inward. So r points in that direction, n points in that direction. Okay. So del g dot n is del g del r. So what is del g del r? So we have g, okay, then we need del g del r. So what is del g by del r? Okay. So that becomes equal to, because I am going to use indices and multiply and so forth, I am going to change the index so that there is no confusion. Okay. So I have minus I k square, here I will use the index t, j t k r dash h t dash k r, then this double sum. Here I will keep m because very soon will become, spherically symmetric. So y m conjugate t theta dash phi dash y m t theta comma phi. Okay. So we have g information, we have del g dot n information, we need del p dot n and p information. Okay. Now the p, which was at xi, the Hankel function has an expansion of this form, which is this entity. Minus p0 summation, I am using a different index here, minus 1 to the power q. Okay. So this is already in a Hankel function form. Why am I doing it? I want to separate within xi we have this r minus d. Okay. So I am trying to separate that. I will have a function of r, I will have a function of d, that is the idea. Okay. So what would that be? Minus 1 to the power q, 2q plus 1, jq of r, kr, then hq of kd, pq cos theta. Okay. The reason it becomes very simple is that we are moving on a sphere, okay, and the field is phi symmetric, axisymmetric. So phi does not come into the picture, theta comes into the picture, that is why it is pq cos theta, and r comes into the picture. Okay. So this d is straight away on a certain axis which gives phi symmetry, okay, and therefore r requires only the radial coordinate and theta, no phi. So this expression now ends up as looking like this. it's in terms of r, the radius, okay, and it's in terms of theta, pq cos theta, and it of course it is in terms of the distance of the source, which is d. So all that was packed in xi has been separated out in a expansion, that is the idea. Okay, so we have p also as a function of r and theta. Now last is of course del p del r, okay, or in fact del p del n, which is del p del r, okay, for the KH integral, that is minus p0 k. I am using another index, minus 1 to the power s 2s plus 1 j dash of s k r h s of k d into p s cos theta. This is the fourth bit. Okay. So now I can do this integral p at a certain r dash is equal to integral over the spherical surface okay of r dash. Let me see, what did I do? Okay, spherical appeared r, this is going to be r now, not dash, r, okay, r dash equal to a, and what is that? I have g r dash del p dot n minus p del g dot n ds. Okay. So if I do that, let us see g del p, this term here. Okay. So g del p dot n, g is now minus, and the integral comes in 0 to 2 pi for phi, 0 to pi, okay, then ik summation j n of k r dash keep on shifting. Sorry, this is r dash, and this r will go to a. Okay. So let us see, we are going to inquire at r dash, we are going to inquire at r dash, and r dash will be less than r, okay, and that is why the expansion for r dash has a Bessel and r has a Hankel, okay, and r is the integration on the surface. So where we have r, it will become a, okay. So jn k r dash, the inquiry point h n of k are equal to a, the surface, and this double sum over m y m conjugate n y m n, okay, theta dash phi dash theta phi, etc. And another term comes in, which is del p del n, which is minus p0 k summation over s minus 1 to the power s 2s plus 1 j dash s k r h s of k d into into PS cos theta A square sin theta d theta d phi. Okay. So phi is this azimuthal coordinate, theta runs from theta equal to 0 to theta equal to pi, this way, and this is the area element on a sphere A of radius A. Okay. So this is G del P del N. Then I have minus P del G del N, minus 0 to twice pi integral 0 to pi, okay, then P, okay, and del G del N or del G del R. So let me write del G del R first, okay. So del G del R, let me look at that. Del G del R was this, let me just bring it in here. Let me bring this whole thing, we'll see. Okay, so we have both P del G del N over here. So let me bring it down first. I will copy. Okay. So del G del R looks like what? Minus IK square. Let me copy this. So if I erase this and I bring this further down, okay, so that is del G del R. Then if I close the bracket here and I remove this, let's say, I bring this up, A square sin theta d theta d phi. Okay. So this is the whole KHIE integral in front of us. Okay. Now the problem posed is axisymmetric. It has phi symmetry. Okay. D here is just a scalar value. D is a scalar value. The only place we have phi is in Ym star, and n has theta dash phi dash. Only here is phi, which is in the form of e to the power of minus or plus Im phi. Okay. Nowhere else is there phi. So if m is 0, it is, I will get a twice pi. If m is non-zero, it is a 0. So m has to be 0. So in this summation over here, m has to be equal to 0. One term has to be picked up. Same here, m is equal to 0. Only one term gets picked up. Okay. So if, and 2 pi gets added. Okay. So now if we do that, what do we get? We must remember from our previous derivations that this particular relation exists somewhere. Let me write it. Y 0 n of theta comma phi is 2n plus 1 by 4 pi p n cos theta delta m0. Okay. So now if I use this twice pi integral here and here on the phi part that is there in here, okay, so what I will get is this. What I will get is this. So what will I do? Let me write that now. Okay. So that is going to be written as, let's see, minus integral 0 to pi ik summation over n jn of kr dash hn of ka. Now this is only m equal to 0. So I get square root of 2n plus 1 by 4 pi p n cos theta dash from here. Then what do we get? Then again we get root over pi into 2n plus 1 p n cos of theta. This is the resultant of the integral from 0 to 2 pi. So it was looking similar to this but had a 2 pi in the numerator. The 2 pi goes into 4 pi square. This 4 pi takes out 4 pi and a pi remains, that is this pi over here. And there is a delta m0, that is why the m here has disappeared. And that is why the summation here is only m0. Okay, I am hoping you are used to that by now. Okay, so now, so that being the case, the inside over here, okay, what do we get is minus p0k, okay, summation over s minus 1 to the power s 2s plus 1 j dash s ka hs of kd ps cos theta a square sin theta d theta. Okay, and then again we have a minus 0 to 2 pi has been taken care of. So I get a 0 to pi, I get a, so let's say I take this minus and that minus out, so I get a plus. So I have I k square summation over a t now j t of k r dash, the inquiry point h, so this should be a, okay, r is a, this should be a, this should also be A. This should also be A. KA, because we are on the surface R equal to A. Okay. Then H dash T, now KA. Okay, the same thing happens here. Okay, I will get a square root of 2n plus 1 by 4 pi Pn cos theta dash. This will be T, unfortunately, not this will be T, this will be T, 2T, this will be T. Okay, and then the same I get root over pi 2t plus 1 again pt of cos theta, and inside p0. Why? Because the negatives have been taken out. P0 summation over q minus 1 to the power q 2q plus 1 jq ka hq of kd pq cos theta and a square sin theta d theta. Okay. Now we have Pn cos theta dash here, Pn cos theta here, Ps cos theta here, and sin theta d theta here. Nowhere else we have theta. In the second component I have theta over here, and theta over here. So we will use the orthogonality of Pt PQ cos theta. Okay, what is that? I will need this whole thing. So let me carry it, copy, paste. Okay, and the result I am going to use is this integral. Let me just say integral 0 to pi Pn of cos theta and Pq of cos theta sin theta d theta, okay, is equal to 2 over 2n plus 1 delta nq. Okay, so this is the integral I will be looking at. This is Pn cos theta n index, Ps cos theta s index with sin theta d theta. So that will take out the theta integral and replace it with 2 over 2n plus 1 delta nq. Okay, n and q must be the same. ठीक है. So there are two sums over here. One is an n sum, one is an s sum. Okay, of this only one sum will remain. Okay, so how will it look like? It will look like this. I will use the minus. Here. It becomes plus. So I get I p0 k square, I p0 k square, okay, then the summation on n, okay, and so j n of k r dash Hankel n of k a, okay. Now here we have square root of 2n plus 1 by 4 pi p n of cos theta dash, okay, then root of pi 2n plus 1, p n cos theta is gone, this constant is taken care of, this summation is gone, minus 1 to the power n, minus 1 to the power n 2n plus 1 j dash n of k a h n of k d h n of k d, then ps cos theta is gone and I am left with a square and 2 by 2n plus 1, okay. Then I have a minus, this minus here, I have a minus p0 I k square and a summation which I will call it as a t, okay, that does not matter, then j t of k r dash h dash t of k a and square root of 2t plus 1 by 4 pi pt cos theta dash goes away, sorry, pt cos theta dash, then root over pi of 2t plus 1, pt cos theta gets into an integral was pq cos theta, okay. So they have to be the same. So now I get this summation also goes away because t summation is adequate, minus 1 to the power t 2t plus 1 jt of k a h t of k d, then a square and 2 by 2t plus 1, okay. Okay. So now I have to cancel 2n plus 1, 2n plus 1, 2t plus 1, 2t plus 1, then what do I have? Then I have a square, okay. So there is a 2 here that goes with 4 root here, there is a 2 here that goes with 4 root here, there is a root pi here, there is a root pi here, there is a root pi here, okay. So many things go away. So let us see what we get. I get this a square in front, so I get a square p0 I k square, a summation over n j n of k r dash h n of Ka, then Pn cos theta dash. Okay. So this 2 gives me a 2n plus 1. I will save it for later. I get a minus 1 to the power n from here. Then j n dash of Ka, h n of Kd, a square is in front, 2n plus 1. Okay. Similarly, this a square comes in front, minus a square p0 I k square. Okay, the square has been taken care of. Summation over a t, j of t kr dash h t dash of kr. Okay. Then p t of cos theta dash minus 1 to the power t, j t of Ka, h t of Kd, and 2t plus 1. Okay. So now, because t goes from 0 to infinity and n goes from 0 to infinity, we can combine this thing. Okay, term by term we can combine this thing. So if we combine the two, we get a square p0 I k square 1 summation n minus 1 to the power n 2n plus 1. Okay. And then we have, see, jn kr dash, jt kr dash, they are common. So I will get a jn of kr dash. Then I also get a hn kd and ht kd. So I will get one hn kd. Okay. Then I have this part at Ka, and I will write the Ka. This should be an A. Okay, this should be an A. It should be an A. I will not write the Ka part, so I have j dash n hn minus h dash n jn. We have seen this term before repeatedly, okay, into Pn of cos theta. Okay, so let me take this term to the next page. Here. Copy. Paste. Okay, this is the term. Now I have this inside term over here, which we have seen repeatedly. Okay, that is equal to I by k square a square. So what do we have now? A square p0 I k square summation over n minus 1 to the power n 2n plus 1 jn kr dash hn of kd into I by k square a square Pn of cos theta. Okay, so then this I, and that I becomes I square minus 1. So, I have a minus, this k square a square goes with k square a square minus p 0 summation over n minus 1 to the power n 2n plus 1 jn of kr dash hn of kd pn cos theta. Okay, just a minute. Cos theta dash minus, okay, cos theta dash, not cos theta. So, this is cos theta dash, this is cos theta dash, this is cos theta dash, my mistake. Okay. So, now shall we look at, so this is what now? This is the result, of KH integral. What did we do? For a point source, we found the green function del p del n on the surface, then del g del n on the surface and p on the surface, and we constructed the KH integral. And using this knowledge we entered and found a response at a point r dash, vectorially r dash bar or r dash theta dash phi dash, okay, due to a point source which is located d from the center of the sphere, okay. And we started off by a certain expansion. What was that? We started off by this expansion here. Let us take this. What was this here? Let us take this. Okay. We started off with this expansion for the pressure, okay, at a certain radius, at a certain theta, due to a source d from the center, okay. So, what is that? Minus p0 summation over q or summation over n minus 1 to the power q minus 1 to the power n 2q plus 1 2n plus 1 jn. Here we are interested in a location r dash, there we are interested in location r. So, okay, here we have hn kd, there we have hq kd. PQ cos theta we are interested in on the surface at a certain theta location, here interested in theta dash location inside. So, this is the same value, the same expression, So, what does this mean? This expression we got using KH integral on an imaginary surface. And this we got directly from the source, directly analytically from the source. Okay, and therefore that surface is imaginary. You can have an imaginary surface, on that you compute the effects of the source in terms of P and del P dot n, and use that information. If you use that information, you can go in and find pressure at a certain location R dash. Okay, so that surface is imaginary, that is the whole idea. The spherical coordinates that entire section of Bessel functions and spherical harmonics, the details and the free space green function derivation, the Kirchhoff-Helmholtz integral equation and green function, the Neumann kind and the Dirichlet kind, interior, exterior, and the examples of spherical piston or spherical cap on a rigid sphere or a point source on a sphere, okay, scattering. All these have been taken from Fourier acoustics by Earl G. Williams. I have mentioned this before. I will close that lecture here now. Thank you.